Okay, so let's get into a specific example, and let me remind us of what we were supposed to have learned in that general derivation process. So we have a general second order differential. So y double plus p of x, y single plus q of x, y equals 0. So if I can get it in that format, then, okay, and we're given one of our solutions, then we just found that the process to find the second solution is to take the first solution times the lovely integral of e to the negative integral p of x dx and y1 squared of x dx. Okay, so first question is, do we have it in the correct form that we can use this formula? And the answer is not currently. I've got x squared out front, but that's an easy fix. I'm going to divide everybody by x squared. So my equation then becomes y double prime minus 3 over x y prime plus 4 over x squared, y equals 0. And I need to identify some things. So I need p of x out of this. So p of x is that negative 3 over x. And I'm going to say, let's do this. Let's just do e to the negative 3 over x dx. Let's just do that piece first. Got to think of it like an integrating factor, I guess. That would be e to the 3, positive 3, of dx over x, which is e to the 3 of ln of x, which is e to the ln of x cubed, and then I can use my ln properties to show that that's x cubed. Okay, so we got that. All right, let's set up. Let's just, y2 is equal to y1, which was x squared. Then we got the integral of x cubed over y1 squared, so that's x squared squared, dx. So that's x squared integral of, and it looks like 1 over x again. So okay, yeah, so dx over x. So that's x squared ln of x. Okay. So our general solution then would be c1 x squared plus c2 x squared ln of x. Okay, so in this last problem in our lesson today, I went ahead and just set up the general, put reminders about the process, about how do we find the second solution. Okay, so looking at what we are given, we need to divide by x squared. So that's going to give me y double minus 1 over x, y single plus 2 over x squared, y equals 0. Okay. And then I found it was helpful to do the e part first. So e to the negative p of x would be negative 1 over x dx, and that seems very familiar, like we've just done that. So that's going to give me e to the ln of x, which is just plain old x. Okay, so at this point then we have x sine of ln of x In the integral, we have an x up top, x squared sine squared of ln of x dx. Okay, and obviously the x's we can simplify. Okay, so now the conversation is, what do we want to do with that sine squared? That's not in a convenient place. But if we, and this is where I'd say, hey, you've got a reminder of derivative and integration rules. So there's a chart you can refer back to. I might look at it and go, hey, does anything jog your memory? Because sometimes some of these trig derivatives or integrals, we don't encounter that often. And so if you remember from your pre-cal days, your trig days, 1 over sine squared is actually equal to cosecant squared. So I'm going to convert that because cosecant squared is a common integral on our chart. I'll kind of remind us of that. But so we got cosecant squared of ln of x over x, and that's dx. And all right, so reminder then, in the integral of cosecant squared u du is negative cotangent u plus c. So we can take advantage of that. Of course, we have that interesting, what do we do about that x in the denominator and dx, but luckily we get a nice hint with that ln. So if I let u equal ln of x, then du is 1 over x dx. Alright, so x sine of ln of x, and we're converting this into cosecant squared u, and that oddly enough equals du. And so that would equal a negative cotangent u. So x sine ln of x times negative cotangent of ln of x and cotangent u is, yes, it's 1 over tangent u, but normally tangent is sine over cosine, so this one would be cosine u over sine u. And since I'm multiplying by sine, and I'm sine times cotangent, that's going to leave me with a cosine up top. So that will simplify down to negative x cosine of ln of x. Okay, so let's put this together then. So we have y, our general solution is c1, and it was at x sine of x, sorry, sine of ln of x. Whoa, getting excited here. Plus, and then what was the form of that second term? Yeah, yes, it was minus, but the minus is merely a reflection of the constant. So the general format, so C2 would look like x cosine ln of x.